Everyone, today we are going to see next passive devices which are used in the microwave communication circuits. These are phase shifters and terminations. Okay, in several microwave communication circuits, we require to change the phase of a incoming signal because of different reasons, and to acquire a greater power at the output, or because of different applications connected to the circuit, we require different loads, so we require terminations also. So let's see this type of devices which provide this kind of results. So first of all, let's see the phase shifter. As the name suggests, a microwave phase shifter is a two-port device which produces a variable shift in the phase of an incoming microwave signal. So if you input a signal, then the phase shifter will produce changes only in the phase of a signal, not in any other parameter of a signal. So primary job or main or the only job of the phase shifter is to produce a phase shift in the incoming signal. So how it is done? Obviously, for creating such device, we are requiring a waveguide as a basic part because it's a two-port device. So we can use transmission lines also, but waveguide is generally preferred, in which a lossless dielectric slab is placed to produce the phase shift. So to produce this change in the transmission phase angle, now transmission phase angle is changed, not the reflection. So if we talk in terms of S parameters, we know that diagonal elements of S parameters are reflection coefficient. So S11, S22, it's a two-port device, so only two. These are reflection coefficient. So S12 and S21, these are transmission coefficients. So forget about these two. The transmission coefficients phase angle will change. These are complex values, that is magnitude at an angle. So angle will be shifted. That is the job of the phase shifter. Okay, so ideally phase shifters provide low insertion loss. Insertion loss means a power loss ratio. That means how much power is lost is during the device, which happens in every case, even if we don't want, but we are trying to keep it to a minimum level. So phase shifter are really good in providing minimum insertion loss. They are capable of handling high powers. They are also able to provide rapid phase changes. So phase change response is very good, and approximately equal loss in all phase states. So if you are changing a phase by 45 degree, so loss, whatever minimum loss that we are encountering, that will be same for 70 degree also. So irrespective of a change of phase, loss will remain equal for all phases. So as I said, loss of a phase shifter is not a desirable thing, but it is kept to a minimum level, but it can also be overcome using an amplifier stage later on in the circuit. So the lesser the loss, the less power that is needed to overcome it. That's why we are trying to provide minimum insertion loss, and that is done by the phase shifter. The most phase shifters are reciprocal networks, means that they work effectively on signals passing in either direction. So when we talk about directions of passing the signal, that means if we are transmitting, the direction of signal going outwards towards the end of the circuit. If we are using a receiver system, then direction of microwave signal is coming inwards towards a microwave communication circuit. So if you are designing a transceiver, that means transmitter and receiver, you should have a phase shifter which is able to provide a same phase shift in both inwards as well as outwards direction. because while transmitting, phase shift should be required in the outward direction, and while receiving, phase shift may be required in the inward direction. So if we are using transceiver, phase shifter should be able to do that in the both directions. So they are usually reciprocal networks. The various types of phase shifters are microwave, precision rotary phase shifter, microwave integrated circuit phase shifter, reciprocal phase shifter, non-reciprocal phase shifter. So these are basic types, out of which we are going to see only one type, that is precision rotary type phase shifter. Okay, so let's see what is it. So the precision phase shifter is a rotary type of phase shifter as shown in figure. So what does it contain? Let's see. So this diagram is a rotary phase shifter. As you can see, there are three waveguides which are used over here. This is the first one, input waveguide. The second one, output waveguide, and third one is a in between input and output, that is circular waveguide. Okay, so first denoted by first, circle denoted by first, is a rectangular waveguide attached to a transition from rectangular to circular, as you can see in the diagram. In between there is a circular waveguide, then followed by output end, again circular to rectangular transition is there, and it consists of second rectangular waveguide. So input is given to input waveguide. Let's assume TE10, as TE10 is a dominant mode in the rectangular waveguide. Input is given in a TE10 mode, and output we obtain is usually obtained in a TE11 mode because of a phase shift. Okay, so let's see what is inside that. Okay, so let's observe it. So as you can see here, there are three dielectric plates which are inserted. As you can see, at input transition, the dielectric plate has a length equal to lambda by 4, so it is called as quarter wave section. At output side also, lambda by 4 plate dielectric slab is inserted, it is also quarter wave section. And in the middle, a lambda by 2 dielectric plate is inserted, which is rotatable, which is also called as half wave section. Okay, the difference between these three is that the first plate, that is at the input plate, it is at 45 degrees, angled at 45 degrees. So this is at 45 degree, this is also at 45 degree. Okay, we will see that in terms of statements again. And the middle one is a rotatable. So input and output plates, or plates at the input section or output section, those are angled plates, whereas the middle section, which is a larger plate, it is rotatable. Okay, so it's not a fixed one. So let's see. It consists of a circular waveguide containing a lossless dielectric plate of length 2L, which is equal to lambda by 2. So it is called as half wave section. So it is in the middle part. A section of rectangular to circular transition, that is rectangular waveguide into a circular transition containing a dielectric plate of length L, that is lambda by 4. That's why it is called as quarter wave section. Then their plate inside that dielectric plate is oriented at an angle of 45 degree to the broader wall of the rectangular waveguide. A broader wall means, suppose this is your rectangular waveguide. So this is a broader wall, this is a wider wall. So to this wall, this will be 45 degrees. Okay, so this is my plate at a 45 degree to the border wall. Okay, and circular to rectangular transition again contains dielectric plate, lossless dielectric plate with same length, that is quarter wave section oriented at again 45 degrees. That's what I said. So the incident wave having a T10 mode becomes a T11 mode in the circular waveguide section. This happens because phase shift produced by the first dielectric plate angled at 45 degrees. Okay, so because of change in angle, the mode is changed to T11. Then inside a circular waveguide, the half wave section plate produces a phase shift equal to twice that of produced by the quarter wave. So if quarter wave is producing 45 degree, let's assume it is producing 45 degree. Remember, quarter wave section is angled at 45 degree doesn't mean that it is producing 45 degree phase shift. Okay, its location is 45 degree to the broader wall, but the amount of phase shift it is producing is dependent on manufacturing. That is how much phase shift you want. Depending on that, it will be changing. So it depends on incident wave of course. Let's assume it is producing a phase shift of 20 degree. So input quarter wave section is producing phase shift of 20 degree. Then the half wave section produces phase shift twice to that. That means half wave phase shift will be producing 40 degree phase shift. Okay. Again at the output, further 20 degree may be added by the output quarter wave section. So total 80 degree phase shift may be obtained. So if you want to obtain 80 degree phase shift, this is how it can be obtained: 20, 40, 20. If you want 90 degree, the combination will be different. Let's say 22.5, then it will be 45 and again 22.5. So that is how phase shift can be produced. Okay, so dielectric plates are re-tapered at both ends to reduce reflection due to discontinuity. Now tapering means smoothing or lessening the width. So this is called as tapering, lessening the width. Okay, so they are re-tapered at both ends to reduce the reflection due to discontinuity. Because of presence of these plates, waves may reflect within the waveguide. So to reduce this effect of reflection, they are tapered. As you can see in this diagram, the structure is like this one. So that is tapering. So this much height is reduced. This much width is, sorry, height not a height, width is reduced. So this is to avoid the reflection. Okay, as you can see in the diagram BCD, this is, let's say, okay, in the first diagram A, input incident wave, as we have said, EI T10 is in y-axis direction. Now once it enters the input section, that is quarter wave section, then it hits the dielectric plate and it is dissolved into two parts, E1 and E2. Now these two parts are separated by 90 degree. So E1 is parallel to the plate and E2 is perpendicular to E1. Okay, once they enter into the rotary plate, that is diagram C, you can see that this is further dissolved into further two parts, E3 and E4. So what is E3 and E4? This is E3. Again it is parallel to the plate, and E4 is this one. This is perpendicular to E3. Okay. Then finally, after entering into the final output quarter wave section, it is further divided into further two parts, E5 and E6. Now E5 is parallel to the plate and E6 is perpendicular to the, this one is E6, is perpendicular to the E5. Okay, and then the resultant of all these vectors will be somewhere different than the original E. So resultant can be calculated using mathematical formulas. So it will show you that the resultant is phase shifted from the original electric field of an incoming signal. So let's see that how it is done. When T10 mode is propagated through the input rectangular waveguide of the rectangular to circular transition, that it is converted to TE11 because of first quarter wave section. Let EI be the maximum electric field strength of this mode, which is resolved into components E1 and E2. Just as I said, incident wave is resolved into two parts, E1 which is parallel to the plate and E2 perpendicular to E1, which we have seen in the figure. So after propagation through these plates, these components are given by EI is the original one. So E1 will be equal to EI cos 45 because it's parallel to the plate. So cos 45 of original EI, e raised to minus j beta 1 L. L is lambda by 2. Beta is a propagation constant. And E2 is a EI sin 45 because it is perpendicular to the E1. So this is E2. So EI sin 45, this is EI. So EI sin 45 e raised to minus j beta 2 into L. Okay, where E0 is if we consider RMS electric field, then E0 is equal to EI upon root 2. Okay, so that is how it is calculated. The derivation of it we are not going to see in the detail. These are just the formulas directly given. The length L, actually it is adjusted such that the components E1 and E2 remain perpendicular to each other. Okay, so that is equal magnitude but differing in phase by 90 degree. Okay, now these quarter wave sections convert linearly polarized waves into circularly polarized wave and vice versa. So if input is linearly polarized, it will be converted into circularly polarized because of rectangular to circular transition, and if they are incoming at a circular polarization, they will be converted into linear polarization. So after entering into the half wave section, they will be further resolved into two further components, E3 and E4. This is E3, which is given by E0 into e raised to minus j theta, that is phase, additional phase given by the half wave section, into e raised to minus j 3 beta 1 into L, and E4 is similarly calculated. Derivation of this is not important in this particular discussion. So after emerging out of half wave section, these field components E3 and E4 are given in above equations, may again be resolved into further two parts of TE11 mode, polarized parallel and perpendicular to the output quarter wave plate. Now E5 and E6 are given again here. So further phase change of minus j2 theta is added to them. So here it is called as, now propagation is further increased to 4 beta. Okay, you can see that. So at the output end of this quarter wave plate, field components parallel and perpendicular to the quarter wave plate can be expressed as E out. So resultant of all of them is now in the E5 and E6 part. So by the vector geometry, E out is square root of E5 square plus E6 square, which comes out to be root 2 into this formula. Okay, so that is how phase change is obtained using different dielectric slab in the rotary phase shifter. If you want to change the phase, now what is the key point? For changing the phase, you have to rotate the phase rotatable section. So if the amount of rotation you are giving, it will produce a different phase changes in the incoming signal. So as per the requirement, rotate your middle plate, that will produce a desired phase change. Okay, so that is how phase shifter, rotary type phase shifter, precision phase shifter is constructed. So this is very useful in several microwave communication circuits. Now let's see what is terminations. Microwave terminations. These are the precise loads required in the microwave measurements and calibration system. Okay, we have several times called as match termination, or our circuit is terminated into a characteristic impedance. So terminations are usually used for taking a output. That output may be for different applications, Depending on different applications, there will be different loads connected to the system. So sometimes you are just measuring something, trying to calibrate something, or sometimes you are attaching a particular application to it. So different applications require different terminations. At microwave frequencies, this is very important because we don't want to reflect any power back into the device. So most common among them are matched termination, which is frequently used because matched terminations provide maximum power transfer from the device to the output, and variable precision short circuits. Okay, so we will see them one by one. A matched load or matched termination absorb all the power incident on it without reflection. So all the power is absorbed, and that's why it is able to transfer maximum power to the output. In this respect, it is equivalent to absolute black body in microwave range. Okay, if we are using waveguides, usually we use waveguides in the microwave devices or microwave communication circuits. So it is a black body used for termination. On the other hand, if you are using transmission lines, then another transmission line is used at the termination, which is terminated in characteristic impedance of the actual circuit. Okay, the short circuit termination produces adjustable reactive load at the desired point in a microwave line. So let's see the two types. First is matched termination. A matched waveguide termination is constructed by mounting a power absorbing pad or cord, as you can see in the diagram. This one is a attenuating pad, that is a power absorption pad, in the space near the closed end of a waveguide. So this is a shorted end, that is a closed end. Near that, this pad is attached as shown in figure. A typical attenuating card or power absorbing card consists of a powered iron or powered carbon mixed with the binder, and it is deposited on a dielectric strip or porcelain, okay, containing silicon carbide. So that is the type of material used for constructing these pads or cards and constructing these terminations. So iron or carbon mixed with a binder and deposited on dielectric strip or porcelain containing silicon carbide. So this is the basic match termination. This is a movable, that means we can change the termination in this. And if we don't want to use these internal pads, we can go for these three types of terminations. What are these? We will see that. So let's move further. A reflection arising from the end, because it is shorted at the end, as we have seen in the diagram. So when they are shorted, so the waves will be reflected. So these reflections will be minimized by tapering the card. As you saw in the diagram, this is tapering. Okay, it is not a uniform. It is not like this. It's not like this. It is made up like this. So it is tapered for minimizing the reflections from shorted end. Okay. Now this tapering is done at a place where electric field is maximum to have a maximum attenuation. Okay, so reflection should be avoided maximally. That's why at a place where electric field is maximum, tapering is done. A card has a finite thickness. Whatever card we are using, it is having a finite thickness. So reflections will be there from this thickness as well. So to avoid it, we can, instead of using this tapered card, we can attach our terminations to the waveguide itself, which is shown in figure CDE. You'll see that. To avoid this reflection, pad is kept closer to the side wall and its length is increased. So if this is a side wall, pad is kept closer to it and its length is further increased to avoid the reflection. Tunable match termination is also shown in figure B. So this is a tunable match termination. You can move this terminating card or attenuating card further forward or reverse to achieve a desired termination. So that is a tunable one. And this C, D, E, these are the terminations which are not using attenuating pad, but these are containing attenuations or terminations at the side walls or at the edges of your waveguide. So match loads may also be designed as by loading the whole waveguide with the lossy materials. So instead of using a attenuating pad, load the waveguide with lossy materials such as powdered metal, lossy dielectric, wood, sand, etc. as shown in figure CDE. So this is how match terminations are constructed. Now there is another type, that is short circuit termination, variable waveguide short circuit termination. Waveguide short circuit terminations provide standard reflection at desired and precisely measurable position. So this is a basic, Figure A is a basic type of variable waveguide short circuit termination. The basic idea behind it is to provide short circuit by changing the reactance of the termination. Again, you can see this is a waveguide. Inside it there is attenuating pad which is connected. Now it is attached to external knob, tunable knob, which we can rotate or move to adjust the termination. Okay, so let's see the working of it. The simplest form of adjustable waveguide short circuit is shown in above figure A. It consists of sliding block, so it can be moved forward and backwards, of a good conductor such as copper, which makes it as snug fit in the waveguide. Snug fit means closely fit. So waveguide is closely fitted with such copper conductor so that it can be moved easily, as well as it can provide good termination also. Position of a block is varied by means of a micrometer drive which is externally connected. So this is a drive. However, electrical short circuit position deviates from physical short circuit. So even if physical location is this one, electrical short circuit location may be here or maybe here also. Okay, in a random manner owing to erratic contact between the sliding block and the waveguide wall. So when these are closely fit, that doesn't mean it cannot move. This is so close that sometimes while moving it further forward or backward, it will touch the walls of a waveguide, and wherever it touches, there electrical short circuit is obtained. Okay. Furthermore, some power leakage past the block may occur. So because of finite thickness, again there will be reflection and resulting in the power leakage, thereby making reflection coefficient less than unity. So reflection coefficient may not be 0 at all. This is also undesirable. So these problems can be overcome by using choke type shorting plungers as shown in figure B and C. So the figure B and C are choke type shorting plungers. So where you can see there is one more conductor which is placed, and here also entire waveguide is almost filled with the attenuating pad or whatever we call it as a termination, and only small part inside it is allowing the wave transmission in this direction and this direction. Again, this entire part can be movable. So this type of terminations are called as choke type. The length of different terminating pads or terminations is also shown, lambda by 4, that is quarter wave section. And these choke type plungers are used to avoid problems of reflection coefficient being non-zero. So to avoid reflections, choke type terminations can be used. So we have seen different devices which are used for phase shifting and terminations. That's all for today. Thank you.